Okay, thank you, Sumitra, again. Let's continue. And today we start another series of examples, still in the complex plane, mostly on the open unit disk, which are important for our course and also for the focus program. If you have looked at the first few weeks, we talked about Hardy spaces, Dirichlet, Bergman, and all of them are examples of RKHS. And there are more model spaces, which Bill Ross will talk about them, Dobranj-Rovniak spaces. And I mean, there are many examples, all of them live on the open unit disk. We start with, even though I don't know if everybody has participated in the first week or not, I believe the students from Laval who participate in this course, they did not. So I need to repeat and I apologize for those who have already seen this. So we start with Hardy space H2, which is the most classical one, is the mother of all other examples of the open unit disk that we know. In the lectures I gave in July, mentioned there are at least 4 methods to define H2 for equivalent. And each way has its own merits. And when we generalize those definitions, we obtain different spaces. I mentioned just one of them here, which help us very rapidly to show that H2, or more precisely H2 of D, is an RKHS. Here is the definition. So H2 is defined to be the space of function f with the power series expansion A n z n, such that an is in little l2, or the sum from n0 to infinity, absolute value of an squared is less than infinity. So this power series with a restriction on the coefficients. The restriction is easy to see that it implies F is analytic on the open unit disk. And I show more than that. I show evaluation are continuous. But before that, I need to say what is the inner product. The inner product on H2 is a copy of inner product in little L2. More explicitly, this means that we define this to be sum from 0 to infinity an bn bar, where an are the coefficients of f, and bn are the coefficients of g. I mean, I repeat here, f is sum of an zn, g is sum of bn zn. It's very easy to show that it's an inner product, and it's complete because little L2 is complete. So we have a Hilbert space. That's a Hilbert space is an easy exercise. Let me show that. H2 is a Hilbert space. That part is elementary. Also, it's an RKHS. It means that the evaluation functionals are continuous. And to do so, look at absolute value of f of z is absolute value of an zn. Absolute value inside. And then, oh, not squared yet. And then we do the Cauchy-Schwarz is less than or equal to the sum n equal to 0 infinity an squared 1 over n. Zn squared 1 over 2. I make too many mistakes, which I mean is indication that I'm tired now. I try to be more focused. So what is the first sum? Absolute value of an squared, then root square. It's the same thing here, f equal to g. So it's the norm of f. So this is equal to the norm of f in H2. And the other one is absolute value of z exponent 2n. So it's 1 over 1 minus r. R here is mod z squared. And then there is a root square for everything. So root square. So this shows that the evaluation function at point z, z in the disk is bounded. And moreover, an upper bound for that. And moreover, norm of z as a functional from H2 to C is bounded by 1 over 1 minus z squared. Good, we have done this for all previous spaces. And to verify if this is an optimal estimation, as we saw before in 5 examples, it's the only way is to find the kernel. So what is the kernel here? The property of the kernel is this. If you do the inner product of f and kz, you should obtain the value of f at point z. True. And now we use the formula that we had here at the very beginning, this one. F of z at the point z is given by a Taylor series. So on one hand, we know that f of z is given by sum an zn. On the other hand, the question is this: if k of z is also k of z, z will be mixed. We had this problem before. Let me write k of at the point w for not mixing z with w. This is also given by the formula bn wn. And the question is, what are the wn? What are the bn? We have to find them such that no, I don't like the way it's written here. Let me change it this way. I change this to be w. And here, now it's good. Now kw at point z. No, this is good now. I mean, I like this better. Kw has this representation, f has the other representation. And so if I want to use the formula for the inner product, the inner product f and kw based on this is the sum n from 0 to infinity an bn bar. That's good. That's one formula. But on the other hand, I also know that also. I write this formula in terms of W2. Also, f at the point W is the sum n from 0 to infinity an W exponent. It's the same formula as here, but I replace z by W. And what I want is this part to be equal to this part. Therefore, the only choice, the Bn bar should be equal to the Wn. So Bn is W bar exponent n. And now I go back to the formula for Kw at point Z is the sum n from 0 to infinity Bn times Zn. Bn is W bar n. If I put them together, is W bar Z exponent n, and it's 1 over 1 minus W bar Z. It's a very celebrated kernel here. Z and W are in D. Some people call it Cauchy kernel, some people Zigo kernel, and even some Cauchy Zigo kernel. I mean, depends which book you use. In the book which is our reference, Paulsen and Raghupati book, they call it Zigo kernel. But in many other places, you see Cauchy kernel. And anyhow, it's a kernel for the H2 space. And in particular, you see that KZZ is 1 over 1 minus mod Z squared. And so norm of EZ, which is the root square of this, is 1 over root of 1 minus mod Z squared. Go back to the estimation we had. Here it is. It's a very precise estimation. It's a very good one. It cannot do better than that. Equality holds. And remember the previous examples. We had 4 examples in the Sobolev case and 1 in the Paley-Wiener. In just one of them, either Sobolev 2 or Sobolev 3, the estimation was good. In all other cases, we were away from optimality. And here is another example for which we have an optimal estimation. In a sense, the calculation we did are very good calculation. So this is just, I mean, even if I say tip of the iceberg, I have not done the justice. Hardy spaces is a very rich subject, started more than 100 years ago, in 1914 by Hardy, and it's well developed, many theorems on this. Just one page about it is, as I said, it's not even tip of the iceberg. We will come back to this space many times in future, and also to subspaces of it. In particular, model and Dubrange spaces. I just make some comments about this. We saw before, after we finished Sobolev spaces, that if you have a reproducing kernel Hilbert space, and M is a subspace such that M is closed in H. So this is an RKHS with kernel K, call it X to distinguish, I put H here. If M is closed in H, then M by itself becomes an RKHS. And therefore, it has a kernel for itself, KMX. And we explored the relation between this kernel and this kernel, the orthogonal projection of H onto M. If we use this, the theorem we had, the theorem said that K, the kernel for M, is the projection of the kernel for H. And even in the Sobolev case, I invited you to verify this, even though we obtained it explicitly. Now, we want to practice this in the context of Hardy spaces. We know our H is H2, and so what is our M? To do this, here is a definition. A function theta from disk to C is called inner if two properties. F is bounded, the theta is bounded. In technical language, they write theta is in H infinity, but I mean, it means it's bounded. And when it's bounded, we know that the radial limits, when we go to what the boundary exists, we assume that theta of zeta, which is lim r goes to 1, theta of r zeta is unimodular. Almost everywhere. Unimodular means absolute value of theta is equal to 1. Such a function is called an inner function. Well, that's my difficulty here. For those who are familiar with the subject, this is, I mean, a piece of bread for them. It's very easy. And for those who don't know the subject, just giving this definition, it gives no clue what we are talking about. So, but at least let me give an example, maybe the simplest one, of an inner function. The simplest one is theta of z is equal to z or z squared or z cubed, these functions. As you see, all of them are bounded on the disk. And when we go to the boundary, zeta or zeta squared or zeta cubed, they are unimodular. So these are inner functions. Another example, for this function, the 0 is at the origin. Theta of 0 is equal to 0. But if A is a fixed point of the disk, then theta of z is equal to A minus C1 minus A bar z. That's another function which I leave as an exercise for the students to show that it's an inner function. Even exponent of this, I mean, either this or like z squared z cubed, and exponent of this are good too. It's a function which is unimodular on the boundary, bounded, so it's an inner function. So having inner function, we can multiply them together and obtain other inner functions. So it gives opportunities to build more and more. Up to here, it's really elementary, even though it might be strange for you at the beginning of theory. But if you want to go beyond that and recognize the family of inner functions, then you need more tools. The first is the theory of products, how to product infinitely many of them together and still obtain a function. And the second is how to use singular measure to create them. It's another category. There is a theorem which is called the canonical factorization theorem, which gives us all the inner functions. I don't mention write the theorem here for the time being. I don't need that because our goal is to study the abstract theory of RKHS. But from abstract point of view, just stick into these two definitions, these two conditions on the definitions. Theta is bounded, unimodular on the boundary. Now I can tell you what is our M. We consider two families of M. The first family, M is equal to theta times H2. These are called Berling subspaces of H2. And show, I mean, it's based on this unimodular property, it is easy to show that they are closed. That's the easy part. Therefore, it is an RKHS by itself. Question for you, find K. What is the kernel for Berling subspaces of H2? This formula, in a sense, can help you. I mean, you can find the projection and then project the Cauchy-Gigot kernel and find the kernel you are looking for. Direct verification also is possible. I mean, you guess a formula and directly verify that. Second category is the complement of this space. We know that if a subspace is given either closed or not, its orthogonal complement is for sure a closed subspace. So the second category is theta H2, but the orthogonal complement. And to emphasize that the orthogonal complement is taken in H2, it is better to write it as H2 minus theta H2. And for these spaces, there is a special notation. So they don't mix with the K we had above. K theta. They denote these spaces by K theta. K is not for kernel here. I mean, I don't know where it comes from, but they are called model subspaces of H2. Let me look at the program model subspaces. Model subspaces was a part of a program, but it was on week 4 by Stefan Garcia, July 27, 28, 29. The videos are available on the website of Fields Institute if you want to have a look at what this means. I said Bill, I made a mistake, it's lectures by Stefan Ramon Garcia. So these are also closed subspaces of H2, so they have a kernel. And the same question as above, find the kernel for these spaces. And this time, even though I can write here K theta here, this is a bit, I mean, too much K, Z, K theta up there. Usually to distinguish, they write K, Z, theta to say that this is the kernel for the model space. In particular, try to find this one, which is important. And I will talk, not today, I mean, near future, about the generalization of this, which will include this part as a special case when we talk about HB spaces, Lagrange-Rovniak spaces. In the previous case, K theta is a closed subspaces of H2. So we know in advance, without any verification, since it is closed, it is an RKHS. But there are some subspaces like HB, which are not closed in H2, but still we can define a kernel, and on these spaces, the kernel is such that it is complete and it gives us an RKHS. When is this? Week 8. Week 8 means October 5, October 6, and October 7. It's on Lagrange-Rovniak spaces. Lectures will be given by Dan Timothy. You can listen and learn about these spaces we want. Another point which is interesting for us as a course on RKHS is that In all previous examples, all 5, 6 that we have seen up to now, even on these two, which I gave as an example and asked you to explore, we have an explicit formula for the inner product, which means an explicit formula for the norm, and also an explicit formula we obtained for the kernel. So two important pieces of information. Formula for norm, formula for the kernel. We will see later when we talk about HP spaces. In this case, it's rather surprising to see that we have an explicit formula for the kernel, but we do not have, say, a good formula for the norm. So 50% of the information is missing. I don't say that we do not define the norm. Yeah, we will. We will give a way, even a method to calculate the norm. But we do not have an explicit, the word explicit is important. We don't have an explicit formula for the norm. Like the previous one, in all previous cases, all the time, either we had a formula based on an integral formula, the one we just saw, here it is, yeah. By this, I mean an explicit formula. I have an explicit formula for the calculation of the inner product. And if F is equal to G, I have an explicit formula for the calculation of the norm. It becomes something like this. I know how to do it. Previous examples like that. Even this and this is like that. In HB spaces, we will see that we do not have a formula as explicit as we wish for the norm. That's one category of examples. Another category is about local Dirichlet spaces and weighted Dirichlet spaces. I will talk about Dirichlet spaces in a few minutes, but the classical one, there are generalized versions. And it's interesting to know that the other 50% is missing for them. It means that they are RKHS. We know that evaluation functions are continuous. We have an explicit formula for the norm. We do not have a formula for the kernel. It's an interesting phenomenon. So not all the time we have all the information. In some spaces, part of information is missing. Good. So this, when I finish here, just, 2-3 pages about Hardy spaces and some subspaces of it, a subject which is more than 100 years old. And we move to the next one, which is Dirichlet space. Recall the definition of F. We put a restriction on the coefficient. Here is the same, and in the Bergman space is also the same, but we add a weight. If F is given by formula A, N, Z, N, D, Dirichlet, is the collection of function F such that N from 0 to infinity, either N or N plus 1, it really doesn't matter. An squared is finite. So here we have a weight here, and this makes the whole theory different. You remember the first week I said that from a structural point of view, we have just one separable Hilbert space. So if you just look at these guys as Hilbert spaces, there is no difference between H2, D, HB, or even model spaces. All of them are the same. But there are other features which make them different. And the kernels are one of them. So first, to show that this is a Hilbert space standard, I leave it to you. It's not something difficult to show that. I didn't mention the inner product. The inner product, if, oh my goodness. Not again. Okay, good. If f is given by some ANZN and G by some BNZN, this is an indication of how we should define the inner product in D. We should define it such that if f is equal to G, we obtain this combination, which is the norm. So it's defined by n plus 1 AN BN bar. And as you see, if f is equal to G, we obtain the same combination as above. So in other words, the norm of f in the Dirichlet space, norm squared, is AN squared. So that it's a Hilbert space is straightforward, but why functionals, evaluation functions are continuous? Why E at point Z is bounded? We start with f. As before, we take the absolute value inside. If we apply Cauchy-Schwarz here, it's not good because we end up with the combination we had in the Hardy space saving. We'll obtain sum of mod AN squared and times sum of mod ZN 2n squared. We don't want mod AN squared. We want n plus 1 times this. To obtain this, I do this trick. I add here n plus 1 root square AN, and I have to divide by that too. And now I apply Cauchy-Schwarz with this as, say, my xn, this as my yn. So it's less than or equal xn squared sum then root square times sum of yn squared 2n n plus 1 a half. And as you see, n from 0 to infinity. This is precisely what we call normal f at point D. Times this, you can keep it as it is. It really doesn't matter what function is. It's a function of z. But if you are familiar with the development of log of 1 plus t in the calculus 1 or analysis 1, this is the whole thing here is 1 over mod z squared log of 1 over 1 minus z squared, the whole thing root square. But this is not really important. We can write it as a constant which depends on z ft. And so f of z is less than this, implies that Ez is bounded. And I mean, again, an estimation for its norm. Last step is to find our kernel. And we do calculations similar to this one, similar to here this, similar to this one. We know the development of f, we assume the development of kw, we do the inner product, and we explore what dn should be. So similar calculation, I mean, to find kz, but in D. Well, f of z is the sum n from 0 to infinity a n z n. Kz, did I write kz or kw? I think I wrote kw up there, not to mistake. I think it was kw. Yes, kw of z. Kw of z is sum n from 0 to infinity bn zn. Bn, we need to find it. We don't know what it is. The inner product of f and kw in D, by definition, is the sum from 0 to infinity n plus 1 a n b n bar. That's the definition of inner product, which I write it as sum from 0 to infinity a n times n plus 1 with b n bar. This is one thing. The other thing, the same formula as here, I write it with z replaced by w. F of w is also sum from 0 to infinity a n times w exponent n. So that's one formula for the inner product. That's another formula for f of w. And we want these to be equal to each other. Therefore, the only possibility is to have this coefficient to be equal to this coefficient. So f of w is equal to f inner product of kw in D, if and only if for each n plus 1 bn bar is equal to wn. Or bn equal to w bar exponent n divided by n plus 1. Therefore, our kernel is the sum n from 0 to infinity coefficient w bar n plus 1 times zn. And this is the sum from 0 to infinity zw bar, or better, I always wrote w bar z, so let's write w bar z here too, divided by n plus 1. we can leave it as it is, or I mean use this is equal to 1 over wz bar log of 1 minus w bar z. It's not indeed difficult to see why this is the case. Let me explain why this is the case. 1 plus z plus z2 is 1 over 1 minus z. We can consider z to be the real a real number. And then you take the integral of this, say from 0 to z. What do we obtain? So here is z plus z2 over 2 plus z3 over 3. And this becomes log of 1 minus z with minus. True? Either you think it this way, or you say that if you take the derivative of this, you obtain the previous one, and at the point z equal to 0, they coincide. This calculation is valid as long as z is inside t. And now divide both sides by z. So 1 plus z over 2 plus z2 over 3, and so on, is 1 over z. And instead of minus log, write log of 1 over 1 minus z. That's the formula, which I used here. And instead of z, I have w bar z altogether. So this is the formula for kw of z. And if w is equal to z, if w is equal to z, kz of z is 1 over z bar, 1 over z squared mod z squared, log of 1 minus mod z squared. And we know from the first week that the norm of Ez is root square of k z. So it's the whole combination here. Square. And we obtained this before indeed. So again, our estimation is sharp. Here it is. It's rather surprising that, I mean, even in this example, our estimation is sharp, and we will see that in the Bergman space, it's the same story. So here we obtain the formula for norm, formula for the kernel, and we have an RKHS. I mentioned weighted Dirichlet spaces. The reason is this. Here, my definition is based on the coefficient. Here it is. It's based on the coefficient. But there is a reason why I put n or n plus 1 here. And the reason is discovered by, I mean, this formula used by Dirichlet himself in his solution of the Dirichlet equation is integral over d unit disk f prime of z squared d az, or it's more clear here, dx dy, and you normalize 1 over pi. We calculate this integral. And if you do the calculation and use the Parseval identity, you see this is equal to n mod an squared. That is why this Dirichlet was called Dirichlet space. Dirichlet started from here. This is called Dirichlet integral. For the generalization, we can use this formula and put a weight here, another weight. So dw spaces are spaces function f such that 1 over pi, I mean, pi is really not necessary here. The important thing is omega here, omega z, f prime z squared dx dy is less than infinity. true. And the omega is something positive. It can be equal to 0, but not on a big set. That's not our concern here. We can show with the same line of reasoning we saw before, very similar to that indeed, that this is an RKHS. What does it mean? It means that it's a Hilbert space, and in this Hilbert space, the evaluation functionals are continuous. Good up to here. The bad part is that we don't have a formula for K. What is Kz? Of course, except for special cases like W is equal to 1, which gives us the classical case we studied before. In the general setting, we do not have an explicit formula for the kernel. So it's our first example for which we know it's an RKHS, but we do not have a formula for K, but we have a formula for the norm. Completely opposite to this will come probably next week, or the week after, when we study Moore's theorem. And by Moore's theorem, we will see that when we have a kernel, we can construct a space. So we start with the kernel. So kernel is there, it's the first line. We construct a space, but at the end of the day, we have an RKHS for which we do not have a formula for the norm. And there is an interplay between these two made by the great master, Don Saracen. He was the first one who found the bridge between Dirichlet spaces and Dobranj-Rovniak spaces, and showed that in some cases they coincide. And out of this, he deduced lots of interesting results. Hopefully, we'll reach to this at the end of the semester. Thank you very much. For today. If there is any question. Well, if not, we see you tomorrow with who's the lecturer? I forgot. Danielle Girella gives lectures on BMO tomorrow morning at 10. So see you then. Hi, Anatoly.
Thank
How are you doing?
You're fine.